Hello students, this video is about the week 10 notes on hypothesis testing, also known as significance testing. We're going to be talking about why we do this kind of testing and what the rationale is behind it. In basic English, what we're trying to do is trying to figure out how likely something is to occur, and if we observe something that is unlikely enough, can we claim that it should not have happened? Speaking of things that are unlikely, let's talk about ESP. ESP is extrasensory perception. It's something that people have talked about and theorized about for a long time, but there's since been no proof of any type of ESP, extrasensory perception. It's having a psychic ability to know something that can't be observed through the five senses. For example, if I claimed that I could see you right now watching this video and said, hey, stop eating that candy bar or something like that, then that would be extrasensory perception. However, it's very difficult to prove, quote unquote, that ESP doesn't exist because there are a lot of chances, a lot of coincidences that make it seem as if it does exist. One way that we can test to see whether ESP exists is through something called the Zener card test. Zener cards are 25 cards with these symbols that are down here. They're not regular playing cards, they're symbol cards. And they are shuffled and drawn one at a time, and there's 5 of each copy of each card in one Zener card deck. So I draw a card, and I hold it to myself, and I look at it myself, and I say to you, what is this card? And it could be a circle, it could be a plus, could be wavy lines, could be a square, or it could be a Patrick. Anyway, the idea is that I look at it and I can see it, but you can't. So if you guess it correctly, that means you're using ESP. You're gaining the knowledge about this card through some sort of other means other than seeing or hearing or smelling the card. I don't know how that would work. So if the subject does not have ESP, if they don't have any sort of way of figuring out what the card is, we expect them to be right about 1 in 5 times, because you're probably going to guess the card right once out of every 5, because there's 5 different cards in the deck, or 5 different types of cards. Moving on to an actual test of this, the illusionist James Randi, a very famous magician and illusionist, had an experiment on his TV show Exploring Psychic Powers Live. You can click on the link in the notes and you can actually watch this on YouTube. It's actually pretty interesting. He tested psychics to figure out if they had ESP, and this woman, whose name is Valerie Swan, she tried to guess the correct symbol on 250 cards. They had 10 Zener card decks, and they wanted to see whether she could guess any of the cards correctly. So it took a very long time. It took about 2 hours, but she tried her best. And now I want to ask you, what percentage of cards would you think she would need to guess correctly in order to confirm she has ESP, right? Because, if she was simply guessing, it would probably be about 1 in 5, which factors out to about, 50 out of 250. Well, it turns out that's exactly what she got. She got 50 out of 250 right. She got exactly the same number as we would expect if she was just guessing, proving that she probably was just guessing. On the TV show, they offered her $100,000 if she could correctly identify 82 out of the 250 cards. Seems pretty likely, right? Why did they choose 82? Hopefully you keep that in your mind and try to focus on that. Why would they choose 82? There's a statistically reasonable reason. Here's the reason. Now, remember sampling distributions from a couple of weeks ago? Sampling distributions are the distribution of all different samples of a certain amount. So, for example, I would show this person 25 Zener cards and get their proportion. And then I would show the next person 25 Zener cards and then I get their proportion. I would have to choose a number of samples, the more the better, and I would have to figure out how often that percentage, that proportion, differs from 0.2. As you can imagine, most people will get right around 0.2. Some people will get maybe 0.22 or 0.25, something like that. Some people will guess better than average. And some people will obviously guess worse than average. They might guess 0.17 or 17%. They might guess about 15%. These are all just percentages of how many Zener cards they would guess correct. And most of the time, people would get right around this number. Now, if I'm talking about a sampling distribution of 250 cards, that's that 250 here, I would get a standard deviation of 0.0253, about 2.5% plus or minus. So the likelihood of her getting 82 out of 250, that's 0.328. In order to figure that out, we'll find the z-score. Remember z-score from several weeks ago, that's a standardized measure of how weird something is, how far above or how far below. And it turns out that 0.328, which is the percentage of guesses correct, if it's 82 out of 250, that z-score is 5.0593. That's really high. That's 5 standard deviations away from the mean. If a person had 5 standard deviations away from the mean of height, they would probably be about 10 feet tall. That's ridiculous. So it's very, very, very unlikely, nigh impossible, for a person to have that height. And the people who ran the show banked on the idea that it's almost impossible that they would get somebody that would have 82 correct guesses. That's why they chose that number. They were looking for something that was almost impossible, or really impossible. Now let's talk about the meat and potatoes of this week's lesson. Remember, we're talking about significance testing or hypothesis testing. Let's talk about what a hypothesis is. It's a statement regarding the value of a population parameter. Remember, the parameters that we talked about in class were the mean, mu, or the population proportion, that could be p. Or you could talk about standard deviation being a parameter, the standard deviation of the population, that's sigma. All of these different things are things that we usually don't know for a population. Like, we don't know the average weight of every single American. So what we do is we take a sampling of all Americans, we try to do a sampling distribution, and we try to figure out, well, the mean of that sampling distribution is probably about the mean of the population. Same thing with proportions. We never know the actual population proportion of all Americans or all, groups of people. So we try to figure it out using point estimates. All right, there are 2 types of hypotheses that we're going to be talking about in this example, the null hypothesis and the alternative hypothesis. Every time you do hypothesis testing, significance testing, you have 2 different hypotheses, null and alternative. The null hypothesis is accepting what is already given to you, or what is accepted. The parameter is equal to 0.2. That's the accepted value. This is the parameter, the value that we would be getting if people were just guessing. Evidence from our experiment that could prove that the accepted or given information is false is going to be the alternative hypothesis. So you could think of the null hypothesis as status quo, as what everyone believes. And you could think of the alternative hypothesis as the idea that we're trying to disprove something that everybody believes. Alternative hypothesis being another explanation. So null hypothesis is any difference from the accepted value is just by chance. And the alternative hypothesis is saying any difference from the given value is because of some reason, because the value is actually greater than or smaller than that number. All right, here's an example using everyone's favorite snack food, chips. The null hypothesis is a statement about what is accepted as truth. So for example, let's say you go to the store and you get a bag of chips, or the vending machine, as it says here. You could get a bag of chips that says it's 1.5 ounces of chips. So if I'm writing the null hypothesis, that means I believe what it says. I believe the average bag of chips should have about 1.5 ounces of chips. However, the alternate hypothesis, the alternative hypothesis is, this should say HA, let me fix that up, perfect, is a statement about what we want to test. So let's say we look at the bag and it says, 1.5 ounces of chips. I think there's less in here. I think they're trying to, get one over on me. I think they're trying to take my money and maybe give me only like 1.4 ounces of chips. So what I'm going to do is I'm going to buy 20 bags of chips. I'm going to find the average weight of those chips and then see how far that is from 1.5 ounces. Notice that when I'm trying to test a null hypothesis against an alternate hypothesis, I need to collect some sort of data or do some sort of experiment. That data is going to be my evidence, and I'm going to try to use that evidence to say, I believe that the alternative hypothesis makes more sense, or I believe that the null hypothesis makes more sense. In other words, I'm either going to reject the null hypothesis, I'm going to say, no, there's no way that this could happen, or I'm going to fail to reject the null hypothesis. My evidence isn't going to be strong enough to get rid of this. So that's an example using chips. Let's look at some other examples. In 2008, 62% of American adults volunteered their time for charity work. Now, if a researcher believes that this percentage is different today, the accepted value is 0.62. So the P, the proportion of American adults, is going to be 0.62, which is 62%, right? The alternative hypothesis is that that proportion is not 62%. It's something else. Now notice, he said that, he or she said that the percentage is different today. Didn't say higher, didn't say lower, just said different. That's why we're using this not equal to symbol. For number 2, according to a study published in March of 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher wonders if the mean length of a call has increased since then. Since we're saying increased here, that big word, here we said different. Let me underline this here. Here we said different. Here we said increase. That's why in this case, we're saying mu is equal to 3.25 versus mu is greater than 3.25. This increased means I'm supposed to be using greater than. The reason I'm using mu here is because we're now talking about the mean length. Mean, right? So mean, the population mean is mu. The reason that we used p here is because 62%, that's a proportion, so we're talking about p. For number 3, using an old manufacturing process, the standard deviation. Now we're talking about standard deviation, which should make sense to you because that's that symbol down here is sigma. Of the amount of wine put in a bottle is 0.23 ounces. With new equipment, hopefully more, more sturdy, more reliable equipment, the quality control manager believes that the standard deviation has decreased. Since we're talking about decreased here, that's why we're using the less than symbol. Notice one thing about the null hypotheses: they all have an equal sign, and they all have the value that we are supposed to have had. They all have the given value, they all have the accepted value. So whenever you're writing a null hypothesis, that accepted or given value goes there with an equal sign and the correct symbol. If we're talking about proportions, it's going to be p. If we're talking about means, it's going to be mu. In this class, we will not be talking about standard deviations. It was just for the example. Well, let me erase that because you might need to see that in a second. Now, for the alternate hypotheses, notice with these alternate hypotheses, they all have the same exact number. That's 0.62. That 3.25. That 0.23. That number has to be exactly the same when you're writing an alternate hypothesis. And this, the parameter is the same as well. P is the same as here. Mu is the same as here. And sigma is the same as here. The only difference between these two is that we're using some sort of inequality symbol, whether it is not equal to, or greater than, or less than. We never use less than or equal to. We never use greater than or equal to, because if it was equal to, it would be here in this null hypothesis. Okay, so hopefully that tells you a little bit about writing hypotheses. The null hypothesis is always going to have an equal sign. The alternate hypothesis is always going to have an inequality sign, some kind of inequality. Now let's talk about the difference between one-tailed and two-tailed tests. Remember, for the first example, the researcher believed that the percentage is different today. Well, we know that 62% of Americans, that's probably going to be right around here, the mean, but we don't know whether that 62% is too high or too low. In other words, we don't know whether our current percentage is above or below 0.62, above or below the mean of the sampling distribution. So, since we don't know whether it's above or below, we're going to call this a two-tail test. We're looking for area in both the upper and lower tails of this sampling distribution. Now, for the mean length of a phone call, we're talking only about the fact that it increased, that the length of a call increased since, I think it was in 2006. So we're not considering whether the mean length of a phone call decreased, right? It's talking about increased. We're only talking about this tail here. That's why we call it a one-tail test. And for the third example, we say that it's a one-tail test because we're only talking about decreased, right? We're only talking about whether the value actually lies down here. We're not predicting that the value is going to be above 0.23 ounces at all. All right, hopefully that makes sense. So now you know how to write the null and alternative hypothesis, and now you know how to figure out whether it is a one-tailed or two-tailed test. Let's jump into an example. Now, the whole idea of hypothesis testing is to find evidence to disprove a claim about a population's parameter. We're always trying to say whether a population's parameter is what we expect or is not what we expect. In order to do that, we need to collect some evidence. So, in this example, we're saying that the Mars Candy Company says that Snickers bars are normally distributed, and they have a mean of 48 grams, and a standard deviation of 2 grams. We actually think that the bars might be a little bit smaller because every time we open up a bar, we're like, man, this doesn't feel like 48 grams. I feel like I'm only eating like 41 grams. It's not fair. The Mars Company is trying to screw me over. First, we write two hypotheses. So the first hypothesis, the null hypothesis, is going to be based on mu, We're using mu because we're talking about the mean. It says it right here. And we say equals because that's what we do for null hypothesis. And 48 is the value that we accept or we are given as truth. That's that 48 grams. We're not using the standard deviation yet. That's going to come later. The alternative hypothesis is that mu is smaller than 48. Why are we using smaller than? Because we think that bars may be smaller than this, right? That less than or smaller than symbol indicates our belief. Then we're supposed to collect information or perform an experiment. Here, we collected information by buying 40 Snickers bars, and I guess having the time of our lives, just chomping away at these Snickers bars. Trying to determine if the evidence is unlikely enough to prove the claim is wrong. So in our sample, we found the average weight. We weighed all 40 Snickers bars, and we found the average weight to be 47.1 grams. So this is lower than 48. Is that enough evidence to say, I think the Mars company is wrong? I'm not sure yet. I'm going to do what's called a hypothesis or significance test. I'm going to figure out how unlikely it is that my sample is 47.1 grams. And here's the general idea. I'm going to set up a sampling distribution. I'm going to find where on the sampling distribution 47.1 is going to be. I'm going to find the area under the curve, or the probability of that event occurring. And then I'm going to say, based on that probability, whether I believe the Mars company or I don't. All right. That's the idea of unlikely enough. That's the idea that we talked about at the beginning of this presentation. We create the sampling distribution using all of the information that we know. We know that the mean of the sampling distribution is going to be equal to the mean, which is 48. And the standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of n, the sample size. Sample size is 40, so 2 divided by the square root of 40 is about 0.32. It doesn't super matter what we're rounding to. I'm rounding to 2 decimal places here because all of our information that we collected is in whole numbers. So taking it to 2 decimal places is statistically viable. So now we identified that our X bar is 47.1 grams. That's here on this distribution. Now what I can do is I can use normal CDF to find the area under the curve. We're looking for the area here. Let me shade it. The area between the curve and 0 from 47.1 grams down. That area in total is 0.0025. Wow, 0.0025. That's 0.25%. So if we were simply drawing from a regular normal population whose mean is 48, the chances of us getting 40 Snickers bars that have this average is this. This is the probability of us getting the results that we got. Seems pretty low, doesn't it? As a matter of fact, this is significantly low. It's low enough that we say, I don't believe the Mars bar claim. I believe that the Mars bars are underweight. That probability, the thing that I just found, the probability of something as weird or weirder happening, that's called the p-value. P stands for probability. And it's the likelihood of seeing results like the ones that we observed if the null hypothesis were true. Now, we can use this evidence to say there's such a small chance that this happened that we don't believe the null hypothesis. So I can go back to my slide on the null hypothesis and I say, I reject this null hypothesis. My evidence says that it's so unlikely that the mean is actually 48 that I simply reject the null hypothesis. I have evidence to suggest that the weight of these Mars bars is lower. All right. The p-value is something that sometimes students get confused, so I wanted to give you a slide that talks about exactly what p-value is supposed to do. The p-value, as I said before, represents the probability of finding results as extreme as yours, so as extreme as the evidence that you collected, due to random chance. So if it were the case that the mean was actually 48, the probability of us getting that 47.1 is super, super low. The smaller the p-value, the more significant the test result is. That's why we call this significance test, because we talk about how significant the findings are, how low the p-value is. A p-value is always interpreted as a percentage. For example, if I get the p-value of 0.041, that gets converted to a percent by multiplying by 100, 4.1%. There's a 4.1% chance that the observed evidence occurred due to random chance. If the p-value is small, a small p-value tells us that we reject the null hypothesis. So if the probability is low, we don't think the null hypothesis is true. If the p-value is large enough, and we're going to talk about enough in a second, we don't have enough evidence. We're not going to say we accept the null hypothesis. We never, ever, ever say accept. We only say fail to reject, which means we don't have enough evidence to say that the null hypothesis is false. Think about it like putting somebody on trial. A person is either guilty, if you reject the null hypothesis, they're either guilty, or, well, you don't say innocent. You find the defendant not guilty. This works very well for people when I tell them this relationship between guilty and not guilty. We either reject the null hypothesis, we think the null hypothesis is guilty, or we fail to reject the null hypothesis. We say that the null hypothesis is not guilty. Statisticians generally use 0.05 or 5% as the boundary for p-values. So if the probability or the p-value is larger than 5%, we're good to go. We fail to reject the null hypothesis. We don't have enough evidence to reject it. If that p-value is less than 5%, that means that we're able to reject the null hypothesis. We don't believe what they're telling us. So let's take a look at the example using 7-Up. Can of 7-Up says 355 milliliters right there on the can. It says it. However, a quality control engineer is worried that the filling machine is miscalibrated. In other words, it's giving more or less soda than it's supposed to. She wants to make sure that the machine is not under or overfilling. You can see this under or over. This should make sense to you. This should indicate to you that we're dealing with a possibility of either higher or lower. That means we're going to be using this not equal to sign. So she randomly selects these 9 cans of 7-Up and measures the contents. These are all the amount of soda in milliliters that she gets. Before I evaluate this, before I find a sample mean for this, I'm going to write down the null and alternative hypotheses. The null hypothesis is that the mean, mu, right? We're talking about the mean. We're talking about the fact that all the cans are 355 milliliters, right? Then is equal to 355. The alternative hypothesis then is that the mean is not equal to that same number. We're not going to calculate the average just yet. You write the null hypothesis based on the same number here and here, the same symbol here and here, and only changing equals and not equals versus greater than versus less than. We can see that it is a two-tail test because under or overfilling is mentioned, so we're saying not equal to is the thing we're looking for. Step 2 is to determine a test statistic. Remember z-scores from several weeks ago. The z-score tells you how weird something is, how unlikely something is to occur, based on a standard normal curve. So what we're going to do is we're going to figure out our x bar, our sample mean. That's 356.67. That's just by taking all of these numbers, adding them together, and dividing them by 9. So 356.67, that is subtracted from 355. Why do we do that? Because it's x bar divided by mu, the population mean that we believe, which is 355, divided by 3.2, that's the standard deviation, divided by the square root of 9, that's the square root of n, that's the sample size. So you see where everything is coming from. So our z-value is 1.566. I just rounded it to 3 decimal places because, I decided to do that. Also because the data that's given to me, the smallest decimal here is 1 decimal place. Taking to 3 decimal places is statistically sound. So now that we have our z-score, how likely or unlikely it is? Well, let's figure that out. In order to find the p-value, how unlikely or how likely it is, we need to figure out whether it's a one-tailed or two-tailed test. We know that it's a two-tailed test because it said not equal to in the previous slide. So this is negative 1.566. This is positive 1.566. Since the curve is symmetrical, I'm finding the area below the curve and above the curve, below the curve down this way and below the curve up this way for those two areas. Remember that area represents the probability of something like that occurring. So her result, that 356.67, could have is up here, right? That is an unlikely event, but it's equally as unlikely as a can that is unfilled by that same amount. So the probability of 0.0587 is below here, and the probability of 0.0587 is up here. That means we're taking our two p-values, our two areas of the tails and adding them together. That's 0.1174. So let's think about what that means. That means there's an 11.74% chance that the data that we found from our experiment happens due to random chance. Remember that we're always going to be comparing it to 5%. What does that mean? That means that we're able to make a conclusion saying that the p-value is larger than 0.05%. So we fail to reject the null hypothesis. When the p-value is larger than the percentage that we're given, that's 0.05, we fail to reject. So this is the sentence that you're supposed to write. There's not enough evidence to suggest that the machine is underfilling or overfilling cans. For now, we have enough evidence to say that we can't reject that null hypothesis. Let's take a look at one more example. In this example, 46% of Americans said they don't trust the media to report fully, accurately, and fairly. Well, keep in mind that we're talking about a proportion. 525 people stated they didn't trust the media out of 1,010 adults. So this divided by this is going to be our p hat. And this 46%, that's going to be our p, our population parameter. So the first thing we're going to do is write our null and alternative hypothesis. And keep in mind, this 0.46, that's the population parameter. We're only going to be using that population parameter here in the hypotheses. We're not going to use this yet because this is our evidence. The evidence comes later. First, we make the hypotheses. Either the population proportion is equal to 0.46 or it's greater than 0.46. Why are we using greater? Because they talked about whether that amount has increased. So increased uses the greater than sign. So now that we know it's a one-tail test, we can go to step 2, which is using the test statistic. Remember that the z-score is going to be different for proportions and for means. The top is going to be pretty similar. It used to be x bar minus mu. Here we're using p hat minus p. It's the same idea. We're using a statistic minus the parameter divided by this calculation here is the standard deviation of the sampling distribution of the statistic. I'm sorry, of the parameter. It's the same idea as we did before, but we don't have the standard deviation here. We're only given proportions. So when we're working with proportions, this is the formula that we are supposed to use. And this formula will be given to you on your formula sheet. Okay, 0.5198, that's our p hat. 0.46, that's our p. Remember, p is still 0.46. 1 minus p is 0.54. That's 1 minus 0.46. And then we're dividing that by 1,010. We're taking the square root of this whole thing. My suggestion to you would be to try to put this in the calculator one step at a time. Do the numerator first. So this minus this, that's 0.0598. And then the whole denominator all at the same time. That's 0.01568. Then I'm going to divide and I get 3.814. If you're following along with what the z-score actually means, this means that there are 3.8 standard deviations between what we found from our experiment and what we thought was going to happen. That's a lot. 3.8 standard deviations is a lot of space. In order to model that, we'll show it here. The area under the curve in this triangle really should be a lot smaller, right? This triangle should be like from here to here, something like that, because we're dealing with a z-score that is 3.814. So if we're trying to find the p-value for that test statistic, we just use the normal CDF function in our calculator. 3.814 would be here. We're going to 10 to the 99th, which is up here. That's in positive infinity. We're using 0 and 1 because this is a standard normal distribution. We found our z-score, so we're using a standard normal distribution. And our p-value is super duper small. If you did this on your calculator at home, you would have gotten 6.8 something times 10 to the negative 5. Since it is so small, you could probably guess what we're going to do. A small p-value means we reject the null hypothesis. There's enough evidence to suggest that the percentage has increased since 1997. We no longer believe this. We reject it. It's not that we're accepting this. We're just rejecting the fact that that p is equal to 0.46. All right, that was the week 10 notes on significance and hypothesis testing. On your test, please be ready to do hypothesis testing for means and for proportions, but you don't have to worry about standard deviations. All right, folks, good luck studying.